The calculus you've learned so far is fantastically useful in the sciences, but is also a significant advance in human thought. It hinges on a productive engagement with the idea of the infinite, both the infinitely large and the infinitely small. Can calculus tell us anything about surfaces or motion in 2 and 3 dimensions? The answer is a definitive yes. In Calculus 3, we'll see how the ideas of Calculus 1 and 2 can be used in 2 and 3 dimensions. There are a couple of useful physical situations that have helped me to better understand the ideas of Calculus 3 that I'd like to share with you in this video. The first is the idea of topography from geography. The second is the idea of fluid flow, like that of a flowing river or a gusty wind. Consider the topography of Walla Walla and its surroundings. In town, near Whitman, it's pretty flat, but out to the east, the terrain quickly begins to undulate. As an avid cyclist, I spend a lot of time out in this area. I love hills. I actually like going up hills on my bike more than I like going downhill.
This is Scenic Loop Road, just east of Walla Walla. It's one of the harder climbs around here for a short bike ride anyway.
On Scenic Loop Road, as I pedal, I'm crossing these thin gray lines. Each line indicates an elevation. Indeed, at every latitude and longitude on Earth, there is an elevation above or below sea level. Just like an abstract surface that depends on two inputs, x and y, and gives an output, z, the topographical surface takes two inputs, latitude and longitude, and gives the elevation as an output. This doesn't seem like a situation where the ordinary derivatives of calculus can help. We'll learn, among many other new ideas, that the slope in this situation depends on the direction you intend to move. Along the direction of the road, the slope of the surface, the topography, is large and positive because the elevation is increasing. However, if I could move perpendicular to the road, the slope would be near zero because the elevation isn't changing that much. In fact, if we travel in the direction of one of the gray lines, the slope will be zero. So there are still derivatives in this context, and they still measure rate of change, but there are additional notions to consider. If you keep the idea of hills and topography in the back of your mind this semester, you'll have a rich and intuitive example to help you understand these new concepts. Another important application and useful metaphor for the ideas we'll be exploring in this class is that of a flowing fluid, like water or air. Here are a few slow motion videos of water features around campus. Some of you may recognize them. Unfortunately, others will have to wait a few months to see them when we return to campus post-COVID. Imagine the water molecules within each of these fluid situations. Each molecule, at each moment in time, has a velocity vector, a vector that describes the molecule's speed and direction. That velocity changes with time, and collectively, the moving molecules result in the flow that you see. This flow occurs in three-dimensional space and can be somewhat predictable or chaotic, depending on the speed of the flow and the obstacles encountered by the water molecules. In the predictable phases, the flow is described by the famous Navier-Stokes equation of fluid dynamics. In the chaotic phase, little is understood, though there are statistical methods that can model the general behavior of the water. In this class, we study the methods needed to quantify systems like this. We show how calculus moves into 3 dimensions to help us understand these systems. In most cases, we'll only study the structure of these systems at a single moment in time. Adding time to the model is something we'll put off until later courses of study. Ignoring time isn't really a serious limitation, however. Systems that don't change much in time, like water flowing in a calm river or through a pipe, can be analyzed by ignoring time. In such cases, like the abstract flow we see here, we can study how much fluid is crossing imaginary boundaries, like the red triangle. We might wonder, for example, is there more fluid flowing into the triangle than flowing out? Once we understand how to do this using vectors, parametric equations, partial derivatives, and multiple integration, we'll be able to study fluid flow, force fields, and a lot of other situations in both 2 and 3 dimensions.